Welcome to Science for Sleepy. Tonight, you and I are drifting far beyond your bedroom ceiling and into the cold, impossible vastness of space. You are tucked in, maybe the blankets are a little too warm, or maybe you're still finding that perfect spot on your pillow. Either way, let me drop a few facts on you that sound like science fiction but are actually true. For example, if you step just a little too close to the planet Jupiter, its gravity could literally stretch you apart like soft dough, a process scientists dramatically call spaghettification. Or consider this, there are more stars in the universe than grains of sand on every single beach on Earth. And here's another one that might make you raise your eyebrows in the dark. 1 teaspoon of a neutron star would weigh as much as every truck, car, train, and ship on our planet combined. You cannot scoop it up with your kitchen spoon, but you can imagine the impossible heaviness tucked inside that little bite. Before we sink too deep into this ocean of strange truths, can I ask you for a tiny favor? Could you slip down into the comments and tell me where you are listening from and what time it is where you are? It always fascinates me to imagine someone in Tokyo drifting off at 2 a.m, while someone in Chicago is listening during an afternoon nap. And, while you're already reaching for your phone, maybe tap that subscribe button too. Think of it as less like subscribing to a channel, and more like reserving your own personal seat on a spaceship that leaves Earth every night. We upload a video every single day, so if tonight's journey doesn't tire you out completely, you can come back tomorrow for another launch. Now, here's the thing about space. The facts are so enormous, so mind-bending, that they almost slip through your fingers like water. Let's start with one of my favorites, Saturn's rings. You've seen them in pictures, wide and elegant, circling that pale giant like some cosmic jewelry. But those rings are not solid. They are made of billions of ice particles, some as small as dust grains, and others as large as mountains. If you could somehow drive a car across the rings, it would be like bumping across endless frozen gravel. Yet from a distance, they look as smooth as a record spinning in slow motion. That illusion of smoothness hides a truth. The universe is messy, jagged, and full of edges. And then there's Venus. You might imagine it as a sister planet to Earth, but let me tell you, it is less like a sister and more like an angry cousin at a family reunion. Its atmosphere is so thick with carbon dioxide that sunlight hits the ground and has nowhere to escape, turning the planet into a furnace hot enough to melt lead. The clouds above are not fluffy and white like the ones outside your window, they are made of sulfuric acid. Imagine rain so corrosive that it could burn through your car roof in seconds. Venus is a planet that looks lovely through a telescope, but would eat you alive the moment you stepped onto its surface. I think what fascinates me most is how much of this is ordinary to astronomers. For them, saying, "Oh yes, a teaspoon of neutron star weighs billions of tons is just another Tuesday." For us, it feels like we're eavesdropping on secrets the universe meant to keep hidden. And as you lie here, letting these facts drift into your thoughts, maybe you start to feel a little smaller, but also a little more connected. Because if the universe can hold sand-like stars and mountain-sized ice chunks in perfect balance, maybe it can also hold your worries for you tonight. So let me leave you with this question as your eyes get heavier. If we are surrounded by truths that sound impossible but are real, how many impossible truths about yourself might also be waiting quietly, just beyond your imagination? You might be lying there now, thinking that space is a vacuum, an endless nothing. We've been told that in space there is silence, the kind of silence so pure and heavy that even the idea of sound feels impossible. And yet, that is not the whole truth. In a way, the universe is far from mute. It hums, it trembles, it resonates in ways we cannot hear with our ears, but can detect with our machines. Astronomers have discovered that black holes, planets, even clusters of galaxies produce vibrations. They are not sounds in the traditional sense, but when translated into frequencies we can hear, the universe reveals a kind of hidden music. One of the strangest discoveries of this kind came from the Perseus galaxy cluster. At its center lies a black hole that has been producing a single low note for about 2.5 billion years. The note is a B-flat, but not the B-flat on a piano you might recognize. This one is 57 octaves below middle C. To give you an idea, the lowest note humans can hear is about 20 Hz. The note from Perseus is 1,000,000,000,000 times lower than that. If sound is vibration, then this is a vibration stretched out so much that one wave can take millions of years to complete. Imagine trying to tap your foot to a beat that takes an entire civilization to hear just once. Scientists describe this in dry language, saying, "It is a B flat, just too low to hear." But think about it. If the universe were a concert hall, then black holes are the organ pipes that never stop playing, humming endlessly in keys we will never detect without instruments. It makes you wonder, is the cosmos in some hidden way always singing? And if so, what other notes are we missing? From the subject of sound, let's drift to light. You've heard the term light year before, but it is worth sitting with it for a moment. A light year is not time, but distance. It is the distance that light travels in 1 year, moving at 186,000 miles every single second. If you could drive a car at that speed, though of course you cannot, you would circle the entire Earth in less than a second. At that same speed, it would take you over 4 years to reach the nearest star beyond our sun, Alpha Centauri. When you look at that star tonight, you are seeing light that began its journey when you were 4 years younger than you are now. Look further, and the time travel becomes more dramatic. The Andromeda Galaxy, the closest large galaxy to our own, is about 2.5 million light-years away. That means the light hitting your eyes tonight left Andromeda when the first ancestors of humans were chiseling stone tools on Earth. Every star is a messenger from the past. The night sky is not a view of now, it is a library of memories, each page delayed by unimaginable distances. When you look up, you are always looking back. And that brings us to motion. Right now, as you lie still in your bed, you are not still at all. You are riding the Earth, which is spinning on its axis at about 1,000 miles per hour at the equator. On top of that, Earth itself is orbiting the Sun at 67,000 miles per hour. Add to that the fact that the entire solar system is orbiting the center of the Milky Way galaxy at about 480,000 miles per hour. And then there's another layer. The galaxy itself is moving through the universe at around 1.5 million miles per hour. You are not just lying down, you are a passenger on a ride so fast and so enormous that even roller coasters would feel embarrassed to compare themselves. But here's the strange part, you feel none of this. You don't feel the spin of Earth. You don't feel yourself slingshotting around the sun. The motion is too vast, too constant, too smooth. Imagine if I told you your bed was moving down the street at 500,000 miles per hour. You would probably grab onto the edges. But because it is happening on a cosmic scale, all you feel is stillness. The universe has a way of moving us without our consent, carrying us along quietly. Now let me tell you something about your body. Everything inside you, your skin, your blood, your bones is made of stardust. This is not a metaphor. The carbon in your cells, the iron that flows in your blood, the calcium in your teeth, all of it was forged inside stars. Billions of years ago, when massive stars reached the end of their lives, they exploded in supernovas. These explosions created the heavier elements, scattering them across space. Some of those atoms drifted and joined together, forming new stars, new planets, and eventually, you. So when you say you are tired, it is not just you, it is the atoms of long-dead stars taking a rest. Astronomer Carl Sagan once said, "We are made of star stuff." It sounds poetic, but it is simply factual. It means the line between you and the universe is thinner than you imagine. You are not separate from the night sky. You are part of it, carried in the same processes that shaped galaxies. Think of it like this. When you look up at the stars, you are not just looking out. You are also, in some small way, looking back in. The universe made you, and now you are gazing at your ancestors burning billions of miles away. Sometimes I like to imagine a star exploding, scattering atoms, and one of those atoms eventually making its way into your bloodstream, flowing through your heart right now. A star that died before Earth even existed could be pulsing inside you at this very moment. That is not fantasy, it is physics. And maybe that is why stargazing feels so calming. It is not just pretty lights in the sky, it is recognition, it is reunion. When you put all these truths together, the universe's deep hum, the time travel of light, the furious speed of your silent journey, and the ancient stardust inside you, you realize that space is not just out there, it is also in here, in your lungs, your veins, your bones. The cosmic and the personal are not as separate as they seem. The universe does not only stretch outward into infinite distances, it folds inward until it reaches the quiet place where you are lying now. And so, as your eyes begin to grow heavier and the sound of my voice softens, I want to leave you with a thought. If a black hole can sing endlessly in a note no ear can hear, and if a beam of starlight can travel millions of years just to brush your cheek tonight, then what kind of quiet messages are your own atoms carrying? What stories are locked inside the stardust of your bones, waiting for you to dream them into being? You might think of planets as variations of Earth, a ball of rock, maybe with water, maybe with air, circling its star like a patient satellite. But the truth is that planets are far stranger than your imagination would guess. Some worlds glitter, some burn, some are tilted sideways, and some behave as though they were designed by a storyteller who got carried away with the details. Take the planet called HD 189,733b. That sounds clinical, almost like the name of a product in a warehouse. But what it hides is terrifying and beautiful. This is a world where the winds roar at thousands of miles per hour, so fast that nothing solid could stand against them. And the rain? It is not water, not snow, but shards of glass. Imagine standing on a beach, except instead of sand you feel invisible shards cutting sideways through the air, slashing in horizontal storms. Every gust carries a glittering spray of molten glass particles. The skies of HD 189,733b are a sapphire blue, which sounds almost peaceful until you remember that it is not the blue of calm oceans, but the blue of destruction. Then there are planets that turn precious stones into weather. On the gas giant Neptune, scientists believe it literally rains diamonds. Deep inside the thick atmosphere, methane molecules are crushed under immense pressure. The carbon atoms bond together into crystals, and those crystals fall downward like shimmering hailstones. Picture a thunderstorm where the raindrops hitting your window are not water but diamonds, bouncing and piling in glittering heaps. It is strange to think that while on Earth people fight wars over a handful of gems, the universe casually sprinkles them like confetti in the storms of distant worlds. Not all planetary quirks are about storms and gems. Some are about posture. Take Uranus. Unlike Earth, which spins neatly on its axis, Uranus is tipped so far sideways it practically rolls along in its orbit. Imagine a spinning top that has fallen almost flat, but stubbornly continues to spin anyway. This tilt means that each pole of Uranus spends decades at a time in sunlight, followed by decades in darkness. Imagine living in a place where the sun does not rise or set for 40 years. Children could be born, grow into adults, and never see night. Or they could grow up in unbroken night and never see the day until middle age. It is less like a planet and more like an experiment in patience. Venus, too, has a strange way of spinning. You might think that all planets spin in the same direction, like cars going the same way on a highway. But Venus is the rebel. It rotates backward compared to most others. If you stood on the surface, ignoring for a moment the lethal heat and acid clouds, you would see the sun rise in the west and set in the east. To make things stranger, Venus spins so slowly that its day lasts longer than its year. Imagine trying to measure your age not by birthdays but by how many times the sun rose and set. You would be much older and much more confused. And then, there are worlds that do not even bother with circular orbits. Some planets swing around their stars in stretched out ellipses, meaning they spend part of the year baking close to their star and part of it freezing far away. If Earth had such an orbit, you would spend one season scorching under relentless heat and the next buried under ice, with no gentle spring or autumn in between. It makes our modest tilt and predictable seasons feel like a gift. Some planets are so close to their stars that they are locked in place, always showing the same face, like the moon does to Earth. Imagine living on a planet where one half is locked in eternal daylight, so hot the ground cracks, and the other half is trapped in perpetual night, so cold the air itself could freeze. The only habitable zone might be the narrow twilight band between them, a thin ribbon circling the planet where temperatures are just tolerable. Your entire civilization would huddle in that slim strip, forever watching the blazing day on one side and the endless night on the other. And then there are the rogue planets. These are worlds not tied to any star at all. They drift alone through the galaxy, carried only by momentum and gravity. No sunrise, no sunset, just endless darkness, with whatever heat they have coming from their own cores. Picture a frozen Earth flung out of orbit, wandering between galaxies, its surface covered in ice, but its core still faintly warm. Life could, in theory, huddle underground, heated by geothermal vents, never knowing the concept of daylight. The thought of such lonely worlds makes Earth's steady orbit feel like a rare and fragile balance. What fascinates me most about these strange planets is how casually the universe creates them. A glass storm here, a sideways spin there, diamond rain falling like loose change. These things sound like wild exaggerations, the kind of details you would invent for a fantasy novel. And yet they are real as the ground under your bed. Astronomers catalogue them with calm voices, as though describing the weather report. But for us, imagining them is like trying to picture dreams made solid. It reminds me of the early days of astronomy, when people on Earth looked up and imagined gods and monsters in the sky. Jupiter was a god of thunder, Venus a goddess of beauty, Saturn the keeper of time. Today we no longer see them as gods, but as giant planets with storms and rings. And yet, the strangeness of their realities almost matches the myths. A planet with storms that never end feels no less fantastical than a god of lightning. A world that rains diamonds feels no less strange than a goddess draped in jewels. The myths and the facts are not so different, they just wear different clothing. Sometimes I wonder what it would feel like to actually stand on one of these worlds, to experience their alien weather and tilted skies, to walk in the twilight strip of a tidally locked planet, knowing that a step too far to the west means burning alive in the heat, and a step too far to the east means freezing solid in endless night, or to listen to shards of glass whip across the horizon, a storm that could cut you to ribbons in seconds. These are not places you could ever visit without technology beyond what we can imagine, but they exist nonetheless. The universe is not just cold space, it is a gallery of experiments, some violent, some absurdly beautiful. And as you lie there, letting your eyelids sink heavier, I want you to hold on to this thought. If the universe can make planets rain diamonds, tilt sideways, or wander starless through the dark, what other strange surprises might it still be hiding, waiting for us to discover? When you look at the night sky, the stars seem equal, just little white pinpricks decorating a dark canvas. But the truth is, stars are as different from one another as people are. Some are giants that could swallow our sun whole without noticing. Others are so faint they burn longer than the universe has been alive so far. They live strange lives, some short and violent, others long and quiet, and all of them end in ways that feel almost theatrical. Let's start with the biggest stars. Imagine a star so large that if you placed it where our sun is now, its surface would stretch all the way out to Saturn. That is what astronomers call a red supergiant. Betelgeuse, the bright shoulder star of Orion, is one of these. It is so large that you could line up hundreds of millions of suns inside it. And yet, despite its size, it will not live long. Massive stars burn through their fuel quickly, like bonfires devouring wood. They shine fiercely but die young, collapsing into supernovas that outshine entire galaxies. Our sun, by comparison, is a middleweight, an average star. It is not particularly large or small, not particularly bright or dim. Astronomers like to call it main sequence, which sounds boring but really means it is in its prime, steadily fusing hydrogen into helium at its core. It has been doing this for about 4.5 billion years and will continue for another 5 billion years or so before swelling into a red giant. When that happens, Earth itself will be scorched and swallowed. That feels like a disaster to us, but to the universe, it is simply the normal rhythm of stellar life. On the opposite end of the scale are the tiny stars, the red dwarfs. These stars are small, dim, and stingy with their fuel. While our sun will last around 10 billion years, a red dwarf can last for trillions of years. Trillions, not billions. To put that in perspective, the universe itself is only about 13.5 billion years old. No red dwarf has had time to die yet. Every red dwarf that has ever been born is still burning, quietly, like a candle that refuses to go out. In the far future, long after our sun is gone, and even after galaxies have drifted apart, red dwarfs will still be glowing faintly, keeping the dark at bay. But stars are not just different in size and lifespan. They differ in color too, and the color tells you about their temperature. Blue stars are the hottest, burning tens of thousands of degrees. They blaze fiercely and briefly, living only a few million years before dying in violent explosions. Red stars are cooler, sometimes only a few thousand degrees at the surface. Yellow stars like our sun sit in the middle. The night sky, then, is not simply dotted with white points. It is sprinkled with stars of many colors: blue, red, yellow, even orange, though your eyes often blur them all into white. With a telescope or a photograph, you can see the subtle rainbow scattered above you. And then there are the exotic stars. Neutron stars, for example. These are the corpses of massive stars that exploded in supernovas. What remains is a city-sized sphere with the mass of the sun. A teaspoon of neutron star matter would weigh more than all the ships on Earth combined. They spin at incredible speeds, some turning hundreds of times per second. As they spin, they beam radiation like cosmic lighthouses, creating what astronomers call pulsars. Imagine lying in bed, hearing a ticking sound in the distance, except that tick is the rotation of a star thousands of light years away, its pulse steady as a heartbeat. And stranger still are magnetars, a rare kind of neutron star with magnetic fields so powerful they could wipe the data on a credit card from halfway across the moon. These stars occasionally release bursts of energy so intense that if one went off within a few light years of Earth, it could disrupt our atmosphere. Luckily, the nearest magnetars are far away, but it is comforting and unsettling all at once to know that such raw power exists, humming quietly in the darkness. Stars are not just solitary. Many of them come in pairs, or even trios, orbiting one another in delicate dances. Imagine two suns rising together, one orange and one blue, casting strange double shadows on the ground. On such worlds, sunsets would be complicated and beautiful, the sky painted in two colors at once. For centuries, we imagined our sun as typical, but the truth is that many stars are not alone. If you look out at the night sky, chances are that a large fraction of those stars are bound to a companion, whirling together endlessly. And of course, every star is both a beginning and an ending. In their cores, stars are nuclear forges. They fuse hydrogen into helium, helium into carbon, carbon into heavier elements, layer by layer. When they die, they scatter those elements into space. That is how the iron in your blood, the calcium in your teeth, and the oxygen in your lungs were created. You are literally walking around with pieces of long-dead stars inside you. The stars did not just light the sky, they built you. In the ancient world, people looked at the stars and told stories. They imagined hunters, bears, heroes, and gods placed in the heavens. The Greeks named Orion, Cassiopeia, and Hercules. The Chinese saw dragons and palaces. The Maya used the stars to measure time and mark seasons. To them, stars were calendars, myths, and omens. Today we see them as plasma and fusion, yet the wonder is not so different. We still tell stories about them, though our stories are written in physics and chemistry. The constellations may no longer be gods, but they are no less mysterious. There is also something deeply human about the way stars connect us across time. When you look at Betelgeuse tonight, the light you see left that star more than 600 years ago, when Europe was in the Middle Ages. Some of the stars you see left their homes before the pyramids were built. The night sky is a record of history older than human memory. You are not just looking at stars, you are looking at time itself, stretched across unimaginable distances. And yet, even though they are so far away, stars shape your life constantly. The warmth you feel on your face in the morning is sunlight, photons born in the sun's core millions of years ago. Each photon spent thousands of years bouncing around inside the sun before finally escaping into space, traveling 8 minutes across the void, and finally landing on your cheek as you step outside. The ordinary sunlight that brightens your morning is the end of a journey that began before humans invented writing. Sometimes I wonder, if stars live for billions of years, do they notice us at all? To a star, your entire life is like the flicker of a candle. Civilizations rise and fall in the time it takes a star to blink. Maybe that is why starlight feels calming. It reminds us that our worries, though sharp to us, are brief against the backdrop of stellar time. So tonight, as you settle deeper under your blanket, remember this. The stars you see are not only distant, they are alive in their own way. They are born, they shine, they die, and they give life. They are both destroyers and creators. And when you close your eyes, you are not just drifting into sleep, you are drifting into the same darkness that cradles every star in the universe. And here is the question I will leave you with. If stars can live billions of years, outshining galaxies and forging the matter that becomes us, then what tiny but lasting light might you leave behind in your own brief moment under their watch? When you hear the phrase black hole, you probably picture a terrifying cosmic vacuum cleaner, a monster in space that devours everything in sight. And in a sense, that image is not entirely wrong, but it is not quite right either. Black holes are not hungry mouths constantly searching for planets to swallow. They are simply places where gravity has become so intense that nothing, not even light, can escape. They are not devils of the universe, but rather strange laboratories, where the laws of physics bend in ways that defy our ordinary sense of reality. The story of black holes begins with stars. When very massive stars reach the end of their lives, they collapse. If the star is heavy enough, no force can resist its collapse, and all of its matter falls inward, compressing into an unimaginably small point. This point is called a singularity, a place where density becomes infinite and where the known rules of physics break down. Around this point is an invisible boundary called the event horizon. Cross that line, and there is no coming back. It is not that you are shredded or burned, it is simply that the universe's pathways all lead inward, and no path leads out. What makes black holes so strange is how they warp space and time. Imagine stretching a rubber sheet and placing a heavy ball on it. The sheet curves. A black hole is like dropping an impossibly heavy weight onto that sheet. It curves space so steeply that it becomes a well without a bottom. Light itself follows the curve, which is why black holes appear black. It is not that they are empty, but that light cannot climb back out. But here is the truly unsettling part. Time itself is twisted near a black hole. If you fell toward one, from your perspective, time would seem normal. But to an outside observer, you would appear to slow down, moving more and more sluggishly as you approached the event horizon, until you froze entirely at the edge. You would never seem to cross it. In reality, you would pass through, but the outside universe would watch you hang there forever. A black hole, then, is not just a place of strong gravity. It is a place where time plays tricks. Black holes also spin. Many rotate at incredible speeds, dragging space-time around with them. Near such a black hole, even if you tried to stay still, you would be carried along by the twisted space itself. This region is called the ergosphere, and within it, nothing can remain at rest. Astronomers sometimes describe it like a whirlpool in a river you cannot resist being swept along. What is fascinating is that energy can actually be extracted from this swirling motion, at least in theory. Some scientists think advanced civilizations could one day harness spinning black holes as power sources, tapping into their immense rotational energy. But perhaps the most mind-bending aspect of black holes is what happens inside. Since no information can escape, we cannot look in and see. The singularity is hidden. Some physicists believe that inside a black hole, all the laws of physics as we know them collapse. Others suggest that black holes may be gateways to other universes or to other parts of our own universe. These are speculations, of course, but they hint at how little we truly know. A black hole is less a monster and more a locked door, with mysteries on the other side. The first person to seriously imagine black holes was not a modern scientist, but a man in the 18th century named John Michell. In 1783, he suggested that if a star were massive enough, even light could not escape its gravity. He called it a dark star. The idea was forgotten for more than a century, until Einstein's theory of general relativity in 1915 made it possible to understand how space itself could bend. It took decades more before astronomers accepted that these objects might actually exist. And then, in the late 20th century, evidence began to pile up. Stars orbiting invisible companions, galaxies with mysterious energetic cores, and eventually, in 2019, the first photograph of a black hole's shadow, a glowing ring around a dark center. That photograph of the black hole in the galaxy Métis 7 was not a portrait in the ordinary sense. What we saw was not the black hole itself, but the hot gas swirling around it, heated to millions of degrees as it fell inward. The black hole revealed itself not by shining, but by casting a shadow against the firestorm. For the first time, humanity looked at one of these invisible giants directly, and it looked back at us with silence. Closer to home, there is a black hole at the center of our own galaxy, the Milky Way. It is called Sagittarius A star. It is about 4 million times more massive than our Sun, yet it sits quietly, surrounded by stars that orbit it like moths around an unseen flame. We know it is there because we can track those stars as they whip around something invisible, moving so fast that only an enormous mass could explain it. If you could see it with your eyes, it would not dominate the sky, it would be small and quiet. That is perhaps the most surprising thing. Black holes are not always dramatic. Many simply sit, patient and still, waiting. And yet, when they are active, they can be the brightest objects in the universe. When matter falls into a black hole, it does not simply vanish. First, it swirls into a disk, heating up to incredible temperatures. The black hole itself remains dark, but the surrounding disk shines so fiercely that it can outshine entire galaxies. Some black holes shoot out jets of particles at nearly the speed of light, stretching across thousands of light years. Imagine a cosmic fountain so powerful that it sprays matter across the galaxy. That is what happens when black holes feast. It is easy to imagine black holes as frightening, but I think they are more humbling. They remind us that the universe is not built for human comfort. Space bends, time stretches, matter collapses, and all of it happens with no regard for whether we find it sensible. Black holes are not villains. They are simply the inevitable outcome of gravity taken to its extreme. They are reminders that the universe is stranger than our instincts can grasp. And as you lie there, with your breathing slowing, perhaps there is comfort in that strangeness. If black holes can exist, if they can bend time and swallow light and still be just another part of the cosmos, then maybe the things in your own life that feel overwhelming are also just part of the larger fabric, strange, yes, but not beyond understanding. So let me leave you with this thought. If a black hole is a door we cannot open, what might be waiting on the other side? Is it nothing? Or is it something so new, so alien, that we do not even have words for it yet? When you step outside on a clear night and look up at the stars, you are really only seeing the faintest hint of what lies out there. Those pinpricks of light belong mostly to our own Milky Way galaxy, a sprawling collection of hundreds of billions of stars bound together by gravity, all orbiting around a massive black hole at the center. A galaxy is not just a clump of stars. It is a city of light, a place where suns are born, live, and die, where clouds of gas stretch across thousands of light years, and where dark matter silently provides the scaffolding that holds everything together. The Milky Way is what astronomers call a spiral galaxy. If you could rise above it and look down, you would see a glowing central bulge surrounded by arms that curl outward, like the swirl of cream in coffee. Those arms are not fixed structures, but rather regions where stars are packed more densely, where the traffic of the galaxy slows just enough that clouds of gas can collapse into new stars. Imagine driving on a highway where the traffic bunches up in certain lanes. That is roughly how spiral arms work, a pattern created not by objects themselves but by their collective motion. Our solar system sits far from the center, out in one of those arms, called the Orion Arm. That might sound romantic, but it is actually just a quiet neighborhood compared to the bustling galactic core. At the center of the Milky Way, stars are packed so tightly that the night sky would blaze with light if you lived there. Here, though, we have dark skies and long silences between the stars, which is probably fortunate because it gives us space to breathe. Galaxies come in many shapes. Some are neat spirals, like ours, with arms curling gracefully. Others are elliptical, more like glowing spheres, filled with older stars and little gas. Then there are irregular galaxies, lopsided and chaotic, as though they were shaken and never put back together. These forms are not just aesthetic quirks, they reveal histories. A spiral galaxy has likely lived a quieter life, slowly forming stars. An elliptical galaxy often shows the scars of violent collisions, when two galaxies smashed together and merged. Yes, galaxies collide. Despite their enormous size, they are not static islands. They move through space, drawn by gravity, and sometimes their paths intersect. When that happens, the galaxies do not simply bounce apart. They pass through one another, their stars barely touching because of the vast distances between them, but their gas clouds and their gravitational fields interact. The result is chaos, new waves of star formation, distorted shapes, and eventually a new, larger galaxy. This is not a rare event. In fact, our own Milky Way is heading toward a collision with the Andromeda Galaxy, our nearest large neighbor. The two are already on a slow-motion collision course, set to meet about 4 billion years from now. Do not worry, you will not be around to see it. But if you were, the night sky would gradually change. Andromeda, which now appears as a faint smudge if you know where to look, would grow larger and brighter until it spread across the heavens. Over millions of years, the two galaxies would merge, forming a new galaxy, sometimes nicknamed Milkomeda. To you, the stars would still shine, but the sky would look dramatically different. Even though galaxy collisions sound destructive, they are also creative. When galaxies crash, their gas clouds are compressed, triggering bursts of star formation. Entire regions light up with new suns, like fireworks blooming across cosmic distances. In that sense, galaxies are both fragile and resilient. They lose their shapes, but they create new generations of stars in the process. One of the most intriguing facts about galaxies is that they are only partly made of things we can see. The stars, gas, and dust are only a small fraction of their total mass. Most of the weight comes from dark matter, an invisible substance that does not shine or absorb light. We know it is there because galaxies spin too fast to be held together by visible matter alone. Without dark matter, the stars would fly apart like water flung from a spinning bucket. Instead, they remain bound, orbiting around something unseen. Dark matter acts like the skeleton of the universe. It does not interact with us directly, but it shapes the large-scale structure of everything. Without it, galaxies would not exist. You could think of it like the unseen framework in a building, the beams and supports you never notice, but that hold the entire structure in place. Even if you never touch it, you live within it. Galaxies are not evenly spread across the universe. They gather in clusters, groups of hundreds or thousands bound by their collective gravity. These clusters, in turn, connect into filaments, vast threads that weave through the universe like a cosmic web. Between them are voids, enormous empty regions with almost no galaxies at all. From a distance, the universe resembles a sponge or a piece of lace, dense lines of galaxies with yawning gaps in between. If you could step outside the universe and look back, that is what you might see, a delicate network shaped by gravity and time. Our Milky Way belongs to a small group of galaxies called the Local Group. Besides Andromeda, it includes smaller companions like the Large and Small Magellanic Clouds, visible from the southern hemisphere. These are irregular galaxies, messy and small, like scrappy satellites orbiting larger giants. The Local Group itself sits on the edge of something even larger, the Virgo Cluster, a sprawling collection of galaxies tied together by gravity. Galaxies are not just pretty arrangements of stars, they are engines of history. Within them, elements are forged in the hearts of stars and scattered in explosions, seeding the next generations of stars and planets. Every atom of oxygen you breathe, every bit of calcium in your bones, every trace of iron in your blood, was made in galaxies, cooked inside stars, and carried outward by supernovae. Galaxies are the kitchens of the universe, where raw hydrogen is transformed into the ingredients for life. There is something almost poetic about that. You are not separate from the Milky Way, you are one of its creations. Your body is built from the ashes of stars, your life lit by a medium-sized star that is just one among billions. If you think of a galaxy as a city, then you are a citizen, moving through your brief span of time while the city itself endures for billions of years. As galaxies evolve, they change character. Spirals may grow into ellipticals after repeated mergers. Small irregular galaxies may be torn apart by larger ones. Even the graceful arms of the Milky Way will not last forever. Galaxies are alive in their own slow way. They are born, they age, and eventually they fade. And yet, despite their grandeur, they remain quiet to us. When you look up at the faint haze of the Milky Way across the night sky, you are seeing only a fraction of its stars. The rest are hidden by distance or dust. To truly grasp the scale, imagine this. If each star in the Milky Way were the size of a grain of sand, the galaxy would stretch thousands of miles across. That is how enormous and crowded it is, even if your eyes show you only a sprinkling. There is something comforting about lying under the night sky and knowing you are inside something so vast, so ancient, and so interconnected. Galaxies are not just faraway pinwheels, they are the homes of countless suns, countless planets, and perhaps countless other beings who may also look up at their skies with the same sense of wonder. And so, as you let your eyes grow heavy and your breathing steady, consider this. What does it mean to belong to a galaxy? To be a small part of a spiral of stars, one citizen among hundreds of billions, in a city so large that even light takes tens of thousands of years to cross it. When you look at the night sky, each point of light seems timeless, steady, eternal. But stars are not eternal. They are living things, in their own way born, changing, and eventually dying. Their lives may span millions or billions of years, but even the greatest stars burn out eventually. To understand stars is to understand the engines of the universe, for they are the ones who forge the elements, who light galaxies, who shape planets, and who make life possible. The story of a star begins in darkness. In the quiet arms of galaxies, clouds of gas and dust drift for millions of years. These clouds, called nebulae, are vast some stretch across hundreds of light years. From a distance, they look like delicate veils, glowing faintly from starlight, but up close they are thick with the raw material of creation. Hydrogen, the simplest and most abundant element, fills these clouds, waiting to be gathered. Stars are born when gravity pulls the gas together. Imagine a small knot forming in the middle of a drifting cloud. Bit by bit, more gas falls inward, drawn by its own gravity. The knot grows denser, hotter, tighter. Eventually, the pressure at its center becomes so great that hydrogen atoms fuse into helium. This is the spark, the ignition. Nuclear fusion begins, and a star is born. Fusion is the secret of starlight. In the core of a star, the pressure and heat are so extreme that hydrogen atoms, which normally repel each other, are forced together. When they fuse, they release energy, and that energy pushes outward as light and heat. A star, then, is a delicate balance. Gravity pulls everything inward, trying to crush it. Fusion pushes outward, resisting collapse. For most of a star's life, these two forces are in balance, holding it steady. Stars come in many sizes. Some are tiny, faint red dwarfs, barely large enough to sustain fusion. They burn slowly, sipping their fuel, and can live for trillions of years longer than the universe itself has yet existed. Others are giants, dozens of times more massive than our sun. They blaze fiercely, burning through their fuel in only a few million years, like a bonfire compared to a candle. The size of a star determines its fate, and its fate can be gentle or violent. Our sun is an ordinary star, a yellow dwarf. It has been shining for about 4.5 billion years, and it will continue for about 5 billion more. That may sound like forever, but it is only a middle-aged star, quietly burning hydrogen into helium in its core. Eventually, though, even the sun will run out of fuel. When a star like the sun nears the end of its life, its core changes. Hydrogen runs low, fusion slows, and gravity begins to win. The core contracts and heats, reigniting fusion in shells around it. This causes the outer layers to expand. The star swells into a red giant, hundreds of times its original size. If the sun were to become a red giant today, it would engulf Mercury and Venus, and Earth would become a scorched wasteland under its swollen atmosphere. But even that stage does not last forever. Once the fuel is truly spent, the outer layers drift away into space, forming a glowing shell called a planetary nebula. The core that remains shrinks into a white dwarf, a dense, hot ember, no larger than Earth, but with nearly the mass of the sun. White dwarfs shine faintly, cooling slowly for billions of years until they fade into darkness. That is the quiet fate of small and medium stars. Large stars, though, live and die much more dramatically. A star 10 or 20 times the mass of the sun burns furiously. It races through its fuel, fusing not only hydrogen into helium, but helium into carbon, carbon into oxygen, and so on, building heavier and heavier elements in its core. This continues until iron is formed, and then the process stops. Iron cannot be fused into heavier elements without consuming energy, so the star's engine stalls. Without outward pressure, gravity collapses the core in an instant. The result is a supernova. A supernova is one of the most violent events in the universe. In a single moment, the star explodes outward with the brilliance of an entire galaxy. For weeks or months, it can outshine billions of stars combined. The explosion scatters heavy elements into space gold, silver, uranium, and all the complex atoms that planets and people require. Every bit of iron in your blood was born in such a star, ripped free in its dying breath. The remnant left behind depends on the size of the star. Sometimes it becomes a neutron star, an object so dense that a teaspoon of its matter would weigh as much as a mountain. Neutron stars spin rapidly, and some emit beams of radiation that sweep through space like cosmic lighthouses. These are called pulsars, and they tick like the universe's own clock, steady and strange. If the star was even larger, its collapse is so extreme that nothing can stop it. The core shrinks past the neutron stage into a singularity, and a black hole is born. This is gravity at its most absolute, a place where space and time curve so tightly that not even light can escape. From the outside, all you can see is the event horizon, the invisible boundary marking the point of no return. Stars, then, are not just lights in the sky. They are stories of transformation. Born from darkness, they shine, create, and eventually return to darkness. And in their lives and deaths, they make everything else possible. Planets form from the leftover gas and dust around new stars, clumping into rocks and worlds. Life arises from the elements that stars forged. Even your body is a living record of stellar history. The calcium in your teeth, the oxygen in your lungs, the iron flowing through your veins, these were all made in stars. To breathe is to take in the breath of ancient suns. It is humbling to think that stars do not know they are doing this. They simply burn, follow the laws of physics, collapse, and explode. And yet, without their silent labor, there would be no galaxies filled with color, no Earth, no oceans, no you. Stars are indifferent creators, and yet everything you love traces back to them. Tonight, as you lie in bed, you can picture yourself as part of this endless cycle. The atoms in your body were once scattered across space, forged in distant suns, drifting in nebulae, gathered into Earth, and now resting here. Someday, far in the future, those atoms will drift again, perhaps to be woven into new stars or planets. You are part of a story billions of years old, written in the light of stars. And here is a gentle thought to close on. Every time you look at the stars, you are seeing the past. Light takes years, centuries, or even millennia to reach us. The star you see tonight may already be gone, its light only now arriving across the void. When you gaze upward, you are not just looking into space, you are looking into history. When you imagine planets, the first ones that come to mind are probably the familiar 8 of our solar system, arranged neatly in order around the sun. But the universe is far more creative than that. Stars are rarely solitary, and even when they are, the worlds that form around them can be wild, eccentric, and unlike anything we experience on Earth. Some orbit closely, scorched by constant heat. Others drift at incredible distances, frozen in eternal darkness. Some follow strange, elongated paths, swinging close and far repeatedly. Planets are not just spheres of rock or gas. They are the living experiments of gravity and chance. Take Mercury, for example. It is the closest planet to the Sun, a scorched world that endures temperatures over 800 degrees Fahrenheit during the day, yet plummets to nearly minus 300 degrees at night. Its surface is covered in craters and ridges, silent monuments to billions of years of asteroid impacts. Mercury spins slowly, taking nearly 60 days to complete one rotation, while orbiting the Sun in just 88 days. That means its day is longer than its year, a strange reversal that would make telling time utterly confusing if you lived there. Venus is different, and stranger still. Though it is only slightly smaller than Earth, it is shrouded in thick clouds of carbon dioxide, with a surface hot enough to melt lead. Winds whip around its atmosphere at over 100 miles per hour, and the crushing pressure is 90 times that of Earth's surface. And the rotation is backward compared to most planets, so the sun rises in the west and sets in the east. If you imagined living on Venus, you would have to cope with both infernal heat and an upside-down sense of time. Earth, of course, feels tame in comparison. It is a planet of balance, with moderate temperatures, liquid water, and an atmosphere that protects and nurtures life. Our moon, modest and grey, stabilizes our tilt and creates the tides, quietly shaping the rhythm of life. This stability feels ordinary because we experience it daily, but on a cosmic scale, Earth is a remarkable accident of habitability. Mars, with its rusty surface and towering volcanoes, tells a story of a world that might have been more like Earth billions of years ago. Olympus Mons, the largest volcano in the solar system, rises nearly 25 kilometers above the surrounding plains, a silent monument to internal heat and geological time. Mars is dry now, but evidence of ancient rivers and lakes suggests that it once had flowing water and possibly the conditions for life. Its thin atmosphere and cold temperatures remind us that planets are fragile, their ability to support life contingent on delicate balances. Jupiter and Saturn are giants, massive enough to influence the orbits of other planets. Jupiter's Great Red Spot, a storm larger than Earth, has raged for centuries. Saturn, with its rings, seems like a jewel set against the dark of space. These gas giants are not solid worlds, but immense spheres of swirling hydrogen and helium, with moons that could host oceans beneath icy crusts. Europa, a moon of Jupiter, has a hidden ocean that may harbor life. Titan, a moon of Saturn, has lakes of methane, alien yet strangely familiar. These companions are worlds in their own right, orbiting giants that themselves orbit the Sun. Uranus and Neptune, the ice giants, are colder, further out, and tipped into strange rotations. Uranus spins almost on its side, so its poles experience decades of sunlight followed by decades of darkness. Neptune, intensely blue, has winds faster than the speed of sound. These outer planets remind us that not all worlds follow the neat rules we might imagine. The universe delights in odd angles, extreme climates, and eccentric behavior. Beyond our solar system, exoplanets, planets orbiting other stars, open a universe of even greater strangeness. Some hug their stars so closely that they are tidally locked, with one side permanently scorched and the other in endless night. Others orbit in eccentric ellipses, swinging from freezing distance to scorching proximity in a single year. There are planets made largely of diamond, gas giants with winds of thousands of miles per hour, and worlds that orbit not one, but two stars, creating alien skies with twin suns. Rogue planets, unbound by any star, wander the galaxy alone. They drift silently through darkness, neither warm nor illuminated, relying on internal heat to keep their cores molten. Imagine a world adrift in space, carrying its lonely light and mass, untouched by any sun, a cosmic nomad, traveling for billions of years. These planets challenge our very idea of what it means to be part of a solar system, existing without the anchor of a parent star. Moons add yet another layer of complexity. Some are geologically active. Io, a moon of Jupiter, is the most volcanically active body in our solar system. Its surface is constantly reshaped by eruptions, spewing sulfur and molten rock. Europa and Enceladus, moons of Jupiter and Saturn, hide oceans beneath their icy crusts. Enceladus even sprays plumes of water vapor into space, hinting at the possibility of life beneath its frozen surface. In these moons, the universe experiments quietly, hiding potential habitats in plain sight. Planets interact not just with their stars but with each other. Orbital resonances, gravitational tugs, and collisions create dynamic, ever-changing systems. Some planets are slowly spiraling inward, destined to be consumed by their stars. Others may be flung outward, ejected into the darkness of space. In every system, the balance is delicate. A small shift can rearrange the architecture of the entire planetary neighborhood. Even the composition of planets is diverse. Rocky worlds like Earth and Mars contrast with gas giants like Jupiter. Ice giants like Neptune harbor mixtures of water, ammonia, and methane. Some exoplanets are scorched iron worlds, their surfaces melted by stellar heat. Others are shrouded in thick clouds of exotic chemicals, producing rain that would be lethal to humans. The universe has no shortage of variety it creates endlessly, often in ways that defy our terrestrial expectations. And yet, these worlds are more than just curiosities. They are laboratories of physics, chemistry, and time. By studying them, we learn about the forces that shape stars, the formation of solar systems, and the potential for life beyond Earth. Each planet, each moon, carries a story written in its rocks, gases, and orbits, a chapter in the epic tale of the cosmos. As you lie there, drifting closer to sleep, consider this. The planets you see in books or on screens are not the only ones. There are billions upon billions, each with its own story, each participating in the quiet, relentless dance around its star. Some may have skies you could never imagine, seasons that last centuries, oceans of liquid you cannot drink, winds that could tear a house apart. Yet all are real, all are part of the vast narrative of the universe. And here is the thought to carry into your dreams. If stars are the furnaces of creation, then planets are the canvases, shaped by heat, gravity, and time, waiting silently for us to imagine their stories. What strange worlds might exist tonight, far beyond our sight, spinning through darkness, carrying secrets we may never discover. When you think of the solar system, it is easy to picture the planets and moons, those steady, dependable worlds that circle the sun like clockwork. But the solar system is also full of smaller, more chaotic bodies. Asteroids, comets, meteors, and dwarf planets. They are often overlooked because they are small, faint and unpredictable. Yet their influence is immense. They carry the history of the solar system in their cores, and occasionally they remind us of their presence in spectacular ways. Asteroids are rocky bodies, leftovers from the formation of the solar system over 4.5 billion years ago. Most of them orbit the Sun between Mars and Jupiter in what we call the asteroid belt. This region contains millions of rocks, from tiny pebbles to objects hundreds of kilometers wide. These asteroids are like the fragments of a cosmic jigsaw puzzle that never quite formed into a planet. They are ancient, unchanged witnesses to the early solar system, holding clues about how planets came to be. Ceres, the largest object in the asteroid belt, is about 900 kilometers in diameter. Though small compared to Earth, it is large enough to be rounded by gravity, earning it the classification of a dwarf planet. Scientists studying Ceres discovered water ice beneath its surface, hinting that even tiny worlds can have complex histories. Many other asteroids, however, are irregular in shape, jagged, and scarred by billions of years of collisions. Their surfaces are cratered like miniature moons. Each mark a record of violent encounters long past. Some asteroids are not confined to the belt. Near-Earth asteroids follow paths that bring them close to our planet. They are monitored closely, not because they are malevolent, but because their orbits occasionally intersect ours. Most are harmless, but history reminds us that impacts do happen. About 66 million years ago, a massive asteroid struck what is now the Yucatan Peninsula in Mexico. The Chicxulub impact triggered a global catastrophe that contributed to the extinction of the dinosaurs. A single rock, tens of kilometers wide, changed life on Earth forever. Comets are different, composed mostly of ice, dust, and organic molecules. They are sometimes described as dirty snowballs, but that understates their complexity. Comets orbit the Sun in highly elongated paths, spending most of their lives in the distant reaches of the solar system. Occasionally, they swing close enough to the Sun that their ices vaporize, creating glowing tails that can stretch millions of kilometers into space. These tails are not solid, they are streams of gas and dust, illuminated by sunlight, dancing gently against the void. Halley's Comet is perhaps the most famous. Its orbit brings it near Earth roughly every 76 years, and humans have recorded its appearances for millennia. Ancient civilizations viewed it as an omen, while modern scientists study it to understand the building blocks of the solar system. When a comet swings by, it is like a time capsule, carrying material unchanged since the solar system's birth. Some of that material even falls to Earth, sprinkling our planet with ancient particles from the outer reaches of the Sun's influence. Meteors are the fiery, fleeting spectacle that occurs when smaller fragments enter Earth's atmosphere. Most are tiny, no larger than a grain of sand, burning up before reaching the ground. Larger fragments that survive the journey are called meteorites. These rocks can be incredibly old, some formed alongside the planets themselves. By studying them, scientists can learn about the early chemistry of the solar system, the presence of water and organic molecules, and even the conditions that may have led to life on Earth. Meteor showers, those predictable streaks of light in the night sky, are caused by Earth passing through streams of debris left behind by comets. Each streak is a tiny fragment, moving at tens of kilometers per second, burning up high above the surface. Despite their fleeting nature, meteor showers remind us that our planet is not isolated. It is constantly interacting with the material left by other celestial bodies, part of a larger cosmic dance that stretches across billions of kilometers. Even moons are sometimes the result of ancient collisions with these small bodies. Scientists believe our moon formed after a Mars-sized body, often called Theia, collided with the young Earth. The debris from that impact coalesced into the moon, which has since influenced the tides, climate, and even the stability of Earth's rotation. Small bodies, then, are not just passive remnants, they shape planets and life itself. Some asteroids are icy, like miniature comets, while others are metallic, rich in nickel and iron. In the future, humanity may mine them for resources, tapping into the vast stores of material that orbit the Sun. They are time capsules, laboratories, and potential resources all at once, orbiting quietly, waiting for us to notice. There are also the more unusual objects, Trojan asteroids, which share orbits with planets like Jupiter, clustering in gravitationally stable regions. Some even speculate that objects like Oumuamua, which passed through our solar system in 2017, are interstellar visitors, traveling light years before passing briefly near the Sun. The idea that objects from other star systems can wander into ours is both humbling and exhilarating, a reminder that the solar system is not isolated, but part of a galaxy teeming with motion. Even the smallest impacts leave traces. Tiny micrometeorites fall constantly on Earth, accumulating in soil and ice. Each one is a grain of cosmic history, a whisper from the past. They remind us that even the universe's smallest players have a role, and that our planet is connected to the broader cosmos in countless subtle ways. Some comets and asteroids harbor organic molecules, the building blocks of life. Scientists speculate that these bodies may have seeded early Earth with the ingredients necessary for biology. In this sense, asteroids and comets are more than rocks. They are carriers of potential, bridges between the lifeless and the living. The universe sends them to us, sometimes in quiet, imperceptible drifts, other times in spectacular, world-changing impacts. Even the way we track these small bodies is remarkable. Modern telescopes, radar systems, and space missions can measure their shapes, spin rates, and compositions. We have sent spacecraft to orbit asteroids, land on them, and even redirect them slightly. Each mission is a careful study of an object smaller than a mountain but older than Earth itself, offering clues about planetary formation, chemistry, and the dynamic processes of the solar system. In short, the solar system is not just the sun and planets. It is a vast collection of bodies, from the largest planets to the tiniest grains of cosmic dust. Each one plays a part in the history of the system, shaping planets, delivering elements, and reminding us of the restless energy of the cosmos. The quiet hum of their orbits, the occasional bright flash of a meteor, and the slow decay of debris into planets and moons, all of it contributes to the story of Earth and life itself. As you drift towards sleep, consider this. Every shooting star you see is a fragment of history, a tiny messenger from the distant reaches of space, perhaps older than the Earth itself. Every grain of dust that fell from a comet billions of years ago may now be part of you, carried in your blood, your bones, or the air around you. The small bodies of the solar system are not minor, they are fundamental. They are the reminders that even the smallest pieces of the universe have power, influence, and history. And here is the thought to carry into your dreams tonight. If even tiny rocks and icy fragments can shape planets, moons, and life itself, then what unnoticed, subtle forces might be shaping your own world in ways you cannot yet see as you travel outward from the Sun, past Mercury, Venus, Earth, Mars, and the massive giants Jupiter, Saturn, Uranus, and Neptune. The solar system begins to feel less familiar. The planets become smaller, the sunlight weaker, and the gravitational grip of the Sun less dominant. This is the realm of the icy and distant, where the solar system stretches into a vast, sparsely populated expanse, full of frozen worlds, wandering comets, and ancient relics from the birth of the Sun. The first stop in this distant domain is the Kuiper Belt. Imagine a ring, wider and flatter than Saturn's rings, encircling the Sun far beyond Neptune's orbit. This belt is home to countless small icy bodies, remnants from the early solar system that never coalesced into planets. Some are only a few kilometers across, while others, like Pluto and Eris, are more substantial, dwarf planets with their own moons and complex surfaces. The Kuiper Belt is like the attic of the solar system, filled with objects left behind by the creation process, each with its own story. Pluto, once considered the ninth planet, is a prime example. It is only about 2,300 kilometers across, roughly two-thirds the diameter of Earth's moon, yet it has mountains, plains, and ice caps. Its surface is a mix of frozen nitrogen, methane, and carbon monoxide, changing slowly over its long orbit. Pluto's largest moon, Charon, is nearly half its size, making their system more like a double planet. The New Horizons mission, which flew past Pluto in 2015, revealed a world far more complex and dynamic than astronomers had imagined, with glaciers flowing, mountains of water, ice, and possible signs of a thin, transient atmosphere. Beyond Pluto, the Kuiper Belt stretches outward for billions of kilometers, home to thousands of known icy objects, and likely countless more waiting to be discovered. Many of these bodies are in resonant orbits with Neptune, locked into patterns that prevent collisions and maintain long-term stability. These frozen remnants preserve the chemical signature of the early solar system, a snapshot of the ingredients that went into building planets billions of years ago. In this way, the Kuiper Belt is a cosmic archive, quietly orbiting in the darkness, untouched for eons. Further still lies the hypothesized Oort cloud, a spherical shell of icy bodies surrounding the solar system at distances that stretch up to 100,000 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. At those distances, the Sun is little more than a bright star on the horizon, and gravitational influences from other stars and the Milky Way itself can tug objects into new orbits. The Oort cloud is thought to be the source of long-period comets, those that take thousands or even millions of years to complete a single orbit around the Sun. We cannot directly observe the Oort cloud. Its objects are too distant and faint, but its presence is inferred from the paths of comets that appear seemingly from nowhere, plunging into the inner solar system. These icy visitors remind us that the solar system is not confined to the orbits of planets, but extends far beyond, with boundaries that are more conceptual than tangible. The Oort cloud represents the ultimate frontier of the Sun's gravitational influence, a distant halo of frozen history. Even beyond the Oort cloud, the Sun's influence continues in a more subtle form. The solar wind, a stream of charged particles emitted by the Sun, creates a bubble around the solar system called the heliosphere. This bubble shields the planets from much of the galaxy's cosmic radiation, shaping the space environment in which all planets exist. The heliosphere is not fixed. It is shaped by the motion of the Sun through the interstellar medium, forming a bow-like structure at the front and trailing into a long tail behind. In a sense, the solar system is not just a collection of planets and belts, but a living bubble moving through the galaxy. The Voyager spacecraft, launched in 1977, have been humanity's first emissaries to this distant frontier. Voyager 1 entered interstellar space in 2014, passing beyond the heliopause, where the solar wind gives way to the environment of the galaxy. Voyager 2 followed a few years later. These spacecraft carry golden records, messages for potential extraterrestrial civilizations, drifting silently through the vast emptiness. They are tiny travelers in a nearly infinite dark, recording human curiosity as they journey into the unknown. Kuiper Belt objects are not all quiet and frozen. Some have moons, rotate rapidly, and even show signs of past geological activity. Haumea, for example, is a dwarf planet shaped like a stretched rugby ball, spinning so fast that it completes one rotation in just 4 hours. Its rapid spin flings material outward, forming a ring system, one of the few known around a small body. Each object in the Kuiper Belt has its own peculiarities, its own slow-motion drama unfolding over billions of years, unseen and almost imperceptible from Earth. Comets, which originate in the Kuiper Belt or the Oort cloud, are messengers from this outermost region. When they fall toward the Sun, their frozen ices vaporize, forming spectacular tails of gas and dust. These tails are transient, changing shape and brightness over weeks as they swing past the Sun. Comets are travelers from the edges, carrying pristine material from the solar system's formation. They connect the inner, familiar worlds to the farthest reaches, a reminder of how interconnected everything is, even across billions of kilometers. The outer solar system also challenges our ideas of what a planetary system should look like. Beyond Neptune, astronomers have discovered objects on unusual orbits, some highly inclined, some very elongated. These detached objects hint at gravitational influences we may not fully understand. Perhaps a distant, unseen planet, sometimes referred to as Planet 9, tugging on them from afar. The outer solar system, in this sense, is still a place of mystery, a frontier where discovery is ongoing and our knowledge remains incomplete. Even the light in these regions is faint. At such distances, the sun appears little more than a bright star, and temperatures are near absolute zero, with gases frozen solid and surfaces coated in ice. It is a quiet, lonely region, where the passage of time is slow, and changes occur over millennia rather than years. Yet this calm belies its importance. These outer realms preserve the earliest materials of the solar system and continue to supply comets and meteoroids to the inner planets. And as you imagine drifting through this outer frontier, think about the scale. From Earth to Pluto is about 30 astronomical units. From Earth to the outer edge of the Oort cloud could be 100,000 astronomical units. That is nearly 2 light years, an almost unimaginable distance. The outer solar system stretches across a vast emptiness, sparsely populated, yet teeming with history and the slow, deliberate motion of ancient worlds. Perhaps the most humbling thought is this: these distant objects have been orbiting for over 4 billion years, almost unchanged. They have survived the migrations of planets, collisions, and the gradual brightening of the sun. They are silent witnesses to the birth and evolution of the solar system. Each icy body, each comet, each tiny fragment carries a story older than life on Earth, traveling in darkness, mostly unnoticed, yet essential to the cosmic order. And here is the thought to carry with you as you drift into sleep. The boundaries of the solar system are not walls, but gradients, places where familiar warmth fades into the vast icy unknown. What other secrets might be waiting at the edge of the sun's influence, silently orbiting in darkness, holding fragments of history that no human has yet touched? For centuries, humans looked up at the night sky and wondered if planets existed around other stars. The idea was tantalizing but unproven, because distant planets are tiny, faint, and difficult to detect against the glare of their parent stars. It was only in the last few decades that technology allowed us to begin identifying these worlds, known as exoplanets. Each discovery expands our sense of what is possible in the universe and hints at the diversity of planetary systems that exist far beyond our own. Exoplanets come in astonishing variety. Some are scorching giants, orbiting so close to their stars that a year may last only a few days. Others are icy wanderers, taking centuries to complete a single orbit. Some orbit multiple stars, creating skies with twin or even triple suns. Each exoplanet challenges our assumptions about how planets form and what conditions might be possible for life. The first confirmed exoplanet orbiting a sun-like star was discovered in 1995. Its name is 51 Pegasi b, a gas giant similar in size to Jupiter, but it orbits extremely close to its star, closer than Mercury is to the Sun. This was surprising because classical models suggested that giant planets should form far from their stars, in colder regions. This discovery forced astronomers to rethink planetary formation, showing that the universe is often more imaginative than our models. Since then, thousands of exoplanets have been confirmed, with discoveries coming from missions like Kepler and TESS. Kepler, launched in 2009, stared at a fixed patch of sky, watching for tiny dips in starlight as planets passed in front of their stars, a method called the transit method. This approach revealed thousands of planets, many in systems completely unlike our own. Some stars host multiple planets in tightly packed orbits, while others have widely spaced worlds, showing that planetary architecture can vary dramatically. Among these exoplanets, astronomers have identified several categories. There are hot Jupiters, massive gas giants orbiting extremely close to their stars, with temperatures high enough to vaporize metals. There are super-Earths, planets larger than Earth but smaller than Neptune, which may have rocky surfaces or thick atmospheres. Some planets fall into the category of mini-Neptunes, intermediate worlds with thick layers of gas, potentially harboring oceans beneath their clouds. Each classification represents a range of possibilities, expanding our understanding of what planets can be. One of the most intriguing pursuits is the search for Earth-like exoplanets, those with conditions that might allow liquid water to exist on their surfaces. Astronomers define a habitable zone around a star, the region where temperatures allow water to remain liquid. Planets within this zone, particularly around sun-like stars, are prime targets for further study. Yet habitability depends on many factors: atmosphere, magnetic field, orbital eccentricity, and even the star's stability. A planet could orbit perfectly within the habitable zone and still be lifeless if other conditions are unfavorable. Some exoplanets are extraordinarily close to Earth, in cosmic terms. Proxima Centauri b, for example, orbits the nearest star to our Sun, Proxima Centauri, just over 4 light-years away. It lies within its star's habitable zone, raising tantalizing possibilities. But its star is a red dwarf, prone to powerful flares that could strip away a planet's atmosphere, making the conditions harsh despite its location. Even nearby worlds, then, may be more hostile than we hope. Other exoplanets are so exotic that they seem almost surreal. There are planets made largely of iron, dense enough that a teaspoon of their material would weigh billions of tons. Some orbit so close to their stars that they are tidally locked, with one side permanently facing the heat while the other remains in eternal darkness. Others travel on highly eccentric paths, swinging from freezing distance to searing proximity in a single year. The diversity of exoplanets defies our expectations and invites endless curiosity. Some systems contain multiple stars, adding another layer of complexity. Planets in these systems may orbit one star closely, or travel around the entire group of stars in wider orbits. Imagine a sky with 2 suns rising at different angles, creating strange shadows and cycles of light. The very concept of day and night could be alien, reshaping the rhythms of potential life. Such worlds remind us that the conditions we take for granted on Earth, moderate light, seasons, and a single sun, are not universal. Detecting exoplanets requires extraordinary precision. Stars are enormous, planets tiny, and light travels across vast distances. Scientists measure stellar wobbles caused by a planet's gravitational tug, or monitor minute dimming during transits. They analyze the composition of atmospheres by observing how starlight filters through them. Every detection is a triumph of technology and patience, revealing worlds we may never visit but can imagine in remarkable detail. Some exoplanets have been found to have moons, rings, or even clouds of gas and dust that could hint at planetary formation in action. Others may be remnants of violent pasts, scattered from their original positions by gravitational interactions. In this way, exoplanets are living laboratories, showing us how planetary systems evolve and interact over billions of years. Each one is a snapshot of processes that continue unseen in the quiet darkness of space. The search for life beyond Earth often focuses on exoplanets, particularly those with the potential for liquid water and stable atmospheres. While we have not yet found definitive signs of life, the discovery of organic molecules, water vapor, and even seasonal changes in atmospheres offers tantalizing hints. Every observation brings us closer to answering the ancient question: are we alone in the universe? Even if life is rare, the possibility exists on distant worlds orbiting distant suns, quietly spinning in the dark. Future missions aim to study these exoplanets in greater detail. Telescopes, like the James Webb Space Telescope, can detect atmospheric compositions, search for signs of water, and even look for chemical signatures that might indicate life. The dream is not just to find planets, but to understand them, to imagine their skies, their climates, their possible oceans and continents. Each discovery is a window into a world we may never touch, yet can explore with our minds. And as you lie there, letting your eyes grow heavy, consider this. Somewhere in the galaxy, countless worlds are orbiting distant stars. Some are scorching, some frozen, some perfectly temperate. Some may host life forms beyond our imagination. They are out there, quietly moving, obeying the same laws of gravity and motion as the planets in our solar system. Their existence reminds us that the universe is vast, creative, and endlessly surprising. The thought to carry into your dreams tonight is this: the night sky above is not just filled with stars, it is filled with potential worlds, each a story waiting to be discovered. How many of these worlds might resemble our own? How many might be utterly alien? And what does it mean for us, living on a small planet in a quiet solar system, to know that countless others exist, silently orbiting, waiting for us to notice? When you look up at the night sky, most of what you see appears serene and distant. Stars twinkle gently, planets move predictably, and the darkness beyond seems quiet. But scattered across the universe are objects that defy ordinary experience, pushing the boundaries of physics and our imagination. Among the most extreme are neutron stars, pulsars, and black holes, celestial phenomena that challenge even the most sophisticated minds, yet their existence is as real as the air you breathe. Neutron stars are the remnants of massive stars that have exhausted their fuel and exploded as supernovae. When the outer layers are blasted away, the core collapses under immense gravity. Electrons and protons merge into neutrons, creating a sphere just about 20 kilometers across but containing more mass than our sun. To imagine this, picture a city-sized object weighing billions of tons per teaspoon. The density is so extreme that atoms are crushed together. Matter behaves in ways we cannot replicate on Earth, and the laws of physics are stretched to their limits. A neutron star is a paradox of extremes, small yet massive, compact yet unimaginably powerful. Its gravity is so intense that the surface curvature warps space and light around it. If you were standing on a neutron star, a dangerous hypothetical scenario, time would pass differently for you compared to a distant observer. Even light escaping from the surface would be stretched and distorted. Neutron stars are cosmic laboratories, where matter and energy exist in states that are impossible anywhere else in the universe. Some neutron stars are pulsars, rotating rapidly and emitting beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like the light from a lighthouse. To an observer on Earth, the beams appear as regular pulses of light or radio waves, precise to fractions of a second. Some pulsars spin hundreds of times per second, a dizzying rate for an object more massive than the Sun. Their regularity is so reliable that they have been proposed as cosmic clocks, potentially even tools for navigation across the galaxy. The energy released by a pulsar is staggering. Its magnetic fields are trillions of times stronger than Earth's, and its rotation can power emissions detectable across thousands of light years. Pulsars are remnants of death, yet they are far from inert. They rotate, shine, and interact with their surroundings, carving out nebulae, accelerating particles, and shaping the space around them in violent and beautiful ways. Then there are black holes, objects whose gravity is so intense that nothing, not even light, can escape. They form when massive stars collapse, or possibly through other cosmic processes, leaving a singularity, a point of infinite density, surrounded by an event horizon, the boundary beyond which escape is impossible. Black holes are not just theoretical. Their presence can be inferred from the motion of nearby stars, the radiation emitted as matter falls in, and even gravitational waves, ripples in the fabric of space-time caused by colliding black holes. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners, sucking up everything nearby indiscriminately. Objects must cross the event horizon to be consumed. Outside that boundary, gravity behaves according to familiar laws, though with extreme effects. Time slows near a black hole, light bends, and space itself is distorted. The closer you approach, the stranger reality becomes. This is not science fiction. It is the universe operating under the rules of general relativity, quietly and without drama, yet profoundly strange. Some black holes spin, dragging space and time around with them. These rotating black holes can create powerful jets of particles that shoot across space at nearly the speed of light. Others exist in binary systems, pulling material from a companion star, forming accretion disks that glow brightly in X-rays as matter heats up before crossing the event horizon. Black holes can merge, sending gravitational waves rippling across the cosmos, detectable here on Earth by instruments like LIGO. These waves are faint, but carry immense information about the most extreme events in the universe. Neutron stars and black holes are also connected, A neutron star can be pulled apart by a black hole, or two neutron stars can collide, producing kilonovae brilliant explosions that forge heavy elements like gold and platinum. The deaths of massive stars do not end quietly. They reverberate across the galaxy, seeding it with the material that will eventually form planets, moons, and perhaps life. In a very real sense, the universe recycles its most violent events into the building blocks of creation. Observing these extreme objects requires ingenuity. Neutron stars, pulsars, and black holes are invisible, or nearly so, to the naked eye. Scientists rely on telescopes that detect radio waves, X-rays, and gravitational waves. Each detection is a triumph, revealing hidden corners of the universe that cannot be experienced directly. Every signal is a whisper from extremes that challenge human comprehension, yet they arrive at Earth, quietly and consistently, for us to observe. Their properties are not merely exotic, they test the limits of our understanding. The densities, gravities, and magnetic fields involved exceed anything possible on Earth. Scientists use these objects to probe physics under extreme conditions, studying matter, energy, and space-time itself. Each discovery sharpens our understanding of the universe while revealing new mysteries. What is the nature of singularities? How does matter behave inside a neutron star? How do black holes shape galaxies over billions of years? The questions are endless. And yet, despite their extremes, these objects are part of the same cosmic order as the Sun and Earth. They obey gravity, motion, and the flow of time. They are distant, deadly, and extreme, but they are as real as the stars we see twinkling tonight. Every neutron star, pulsar, and black hole is a reminder that the universe is not uniform, predictable, or tame. It is wild, creative, and occasionally terrifying, yet profoundly ordered. Even imagining these objects can inspire awe. Picture a neutron star spinning hundreds of times per second, a city-sized ball of neutrons whose magnetic fields would crush anything familiar to us. Picture a black hole, its event horizon bending light and warping space, silently consuming matter with unrelenting gravity. And yet, these extremes are silent. They do not announce themselves to the cosmos in drama or spectacle, except through subtle signals and occasional bursts of energy. They exist quietly, profoundly real, shaping the universe in ways that often go unnoticed. As you drift towards sleep, consider this. The universe is filled with extremes, and yet you are safe on Earth, in a world governed by familiar physics, untouched by the violent and strange forces that dominate elsewhere. Neutron stars, pulsars, and black holes remind us that reality is far stranger than fiction, and that the cosmos operates on scales and with energies that dwarf human experience. Yet it is all part of the same tapestry, every extreme and every gentle light connected by the same rules of space and time. The thought to carry into your dreams is this: somewhere, right now, a neutron star is spinning rapidly, a black hole is quietly bending space, and the universe continues in a symphony of extremes. How many of these extreme objects exist in our galaxy alone? And what other strange phenomena might be waiting to be discovered in the vast darkness beyond, quietly shaping the cosmos? When you look up at the night sky on a clear evening, you might see a faint milky band stretching across the darkness. That band is the Milky Way, our home galaxy, a sprawling collection of hundreds of billions of stars, along with gas, dust, and dark matter, all bound together by gravity. Galaxies are the grandest structures in the universe, each a cosmic city of stars, each carrying the history of billions of years. They are immense, quiet, and beautiful, yet filled with mysteries that continue to puzzle astronomers. Galaxies come in a variety of shapes and sizes. Some are spiral galaxies, like the Milky Way, with graceful arms winding outward from a central bulge. Others are elliptical, shaped like elongated footballs, and often older and less active in forming new stars. There are irregular galaxies too, which seem chaotic, possibly shaped by collisions or gravitational disturbances. Each galaxy is unique, yet all follow the same fundamental rules. Gravity binds them together, stars form and die within them, and matter and energy circulate in complex dynamic patterns. Spiral galaxies are among the most visually stunning. Imagine our Milky Way as a disk over 100,000 light-years across, with a dense bulge in the center and arms spiraling outward, filled with young blue stars and nebulae where new stars are being born. Gas and dust flow along the spiral arms, interacting with gravity to trigger star formation. Meanwhile, older stars drift into the more diffuse halo surrounding the disk. The Milky Way is not static. It rotates, with stars and clusters orbiting the center at different speeds, creating a dynamic, ever-changing system. At the heart of nearly every large galaxy lies a supermassive black hole. These black holes contain millions or even billions of times the mass of the Sun, compacted into an almost infinitesimal point. Ours, Sagittarius A, sits about 26,000 light-years away from Earth, quietly influencing the motions of stars in the galactic center. While it is currently relatively calm, supermassive black holes can feed on surrounding gas, stars, and dust, creating active galactic nuclei, bright, energetic regions that outshine the combined light of billions of stars. They are the engines of galaxies, shaping their evolution in ways still being studied. Galaxies are not isolated. They interact, collide, and merge in cosmic dances that span millions of years. When galaxies collide, stars rarely crash into one another, because the distances between them are vast, but gas clouds interact, triggering bursts of star formation. These galactic collisions can reshape the structure of the galaxies, turning spirals into ellipticals, stirring matter into tidal tails, and even feeding the central black holes. The universe is not static. It is a dynamic stage where galaxies grow, evolve, and transform over eons. The Milky Way itself is on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor. In about 4 billion years, the two galaxies will merge, creating a massive new galaxy. This future event, though unimaginably slow from our perspective, demonstrates the grand scale of galactic evolution. Such mergers are common in the universe, highlighting that galaxies live in communities and their fates are intertwined through gravity and time. Galaxies vary not only in size and shape, but also in composition. Spiral galaxies tend to have active star formation in their arms, while ellipticals contain older, redder stars and less gas for creating new stars. Some galaxies are dwarfs, containing only a few billion stars, while giants like IC 1101 boast hundreds of trillions. The variation is astonishing, and every galaxy is a record of cosmic history, revealing clues about how stars, gas, dust, and dark matter have interacted over billions of years. Dark matter plays a critical role in galaxies. Though invisible, it exerts gravitational influence, shaping the orbits of stars and the rotation of the galaxy as a whole. Observations show that stars in the outer reaches of galaxies rotate faster than expected based on visible matter alone, indicating the presence of unseen mass. Dark matter, then, is a hidden scaffold, holding galaxies together and influencing their formation, though its exact nature remains one of astronomy's greatest mysteries. Galactic evolution is also influenced by supernovae, the explosive deaths of massive stars. These explosions scatter elements like carbon, oxygen, and iron into interstellar space, enriching the gas that will form the next generation of stars and planets. Without these explosions, galaxies would lack the chemical diversity necessary for planets and life. Every element in your body, every rock, and every breath of oxygen owes its existence, in part, to countless stellar deaths occurring over billions of years within galaxies. Beyond individual galaxies, the universe is structured into clusters and superclusters, vast collections of galaxies bound by gravity. The Milky Way is part of the Local Group, containing over 50 galaxies, including Andromeda and the Triangulum Galaxy. Clusters contain thousands of galaxies, and superclusters stretch across hundreds of millions of light-years, forming filament-like structures separated by cosmic voids. The universe, on its largest scales, resembles a cosmic web, a vast lattice of matter shaped by gravity, dark matter, and the expansion of space. Observing galaxies across different distances is like looking back in time. Light from the most distant galaxies has traveled billions of years to reach us. When we observe them, we see galaxies as they were long ago, revealing the early stages of formation and evolution. Early galaxies are often small, irregular, and rapidly forming stars, unlike the well-ordered spirals and ellipticals seen nearby. Studying these distant galaxies allows scientists to understand how galaxies grow, collide, and mature over cosmic timescales. Even within a single galaxy, stars, gas, dust, and dark matter interact in intricate patterns. Spiral arms host star-forming regions, supernova remnants, and molecular clouds. Central bulges contain older stars, orbiting densely packed regions, influenced by the central black hole. Stellar streams, remnants of smaller galaxies torn apart by gravity, wind through the halo. Each galaxy is a miniature universe in itself, a complex ecosystem of matter, energy, and gravitational forces. And yet, despite their immense scale and complexity, galaxies are ephemeral on a cosmic timescale. Stars die, black holes feed and merge, gas is consumed or expelled, and structures are reshaped by collisions. What seems eternal and unchanging to human eyes is constantly evolving over millions and billions of years. Galaxies are both ancient and transient, simultaneously witnesses to cosmic history and participants in its ongoing drama. As you drift towards sleep, consider this. Your night sky is more than stars. It is the projection of a vast, interconnected cosmic city. Each galaxy contains billions or trillions of suns, each potentially hosting its own planetary systems. Each galaxy has its own past, present, and future, shaped by gravity, dark matter, and the hidden engines of supermassive black holes. And somewhere, right now, galaxies are colliding, stars are forming and dying, and the universe continues its quiet, relentless evolution. The thought to carry into your dreams tonight is this. Galaxies are the grand cities of the universe, each with its own character, history, and secrets. How many of their countless stars have planets orbiting them? How many worlds might host life, or entirely unfamiliar forms of matter and energy? And what might we discover as we continue to look farther, deeper, and more precisely into the vast, star-filled darkness? As you drift ever farther in your imagination, past galaxies and clusters, you enter the realm of the universe itself, its vastness, its history, and its mysterious future. The universe is not static, it is expanding, stretching the fabric of space-time itself. Every galaxy, star, and planet is moving, not merely through space, but with space, carried along in the cosmic flow that began with the Big Bang over 13 billion years ago. The very emptiness between galaxies is growing, subtly but relentlessly, altering distances on a scale almost impossible to comprehend. This expansion was first observed by Edwin Hubble in 1929. By measuring the light from distant galaxies, he noticed a redshift, the stretching of light toward longer wavelengths, indicating that galaxies were moving away from us. The farther a galaxy is, the faster it appears to recede. This simple but profound observation revealed that the universe itself is expanding, a discovery that transformed our understanding of cosmology. Space is not just empty, it is dynamic, stretching like a vast invisible balloon. Even more perplexing is that this expansion is accelerating. Observations of distant supernovae in the late 1990s showed that galaxies are not merely drifting apart, they are moving apart faster and faster. This discovery introduced one of the universe's greatest mysteries: dark energy. Dark energy is an invisible force, making up about 70% of the total energy of the universe, driving galaxies apart against the pull of gravity. Its nature remains unknown. It is not matter. It does not interact with light in a way we can detect, yet its influence dominates the cosmos. Imagine that. The universe itself is being pushed outward by a force we cannot see, measure, or fully understand. Dark energy determines the ultimate fate of everything. If it continues to accelerate the expansion, Galaxies will drift so far apart that each will appear isolated, dark, and silent, with stars burning out over billions of years until only faint remnants remain. The universe could become a cold, empty place, vast beyond imagination, almost entirely devoid of life and light. But there are other possibilities. If dark energy behaves differently over time, the expansion might slow, allowing gravity to pull galaxies back together in a big crunch. Alternatively, the universe might reach a state of equilibrium, expanding forever but at a stable rate. Each scenario is profoundly different, yet all unfold on timescales far beyond human comprehension. Our lives are tiny flickers in the vast cosmic timeline, yet even in that brevity, we can observe, understand, and marvel at these processes. On smaller scales, clusters of galaxies remain bound together, immune to the overall expansion of the universe. Gravity still holds sway locally, creating pockets of structure amid the stretching void. Galaxies collide, stars are born and die, black holes merge, and supernovae scatter elements. But on the grandest scales, the universe is slowly separating, an intricate dance of matter and energy, governed by forces we are only beginning to understand. The cosmic microwave background radiation, the faint glow left over from the Big Bang, is our window into the early universe. Detected in 1965, it is uniform yet slightly irregular, revealing the seeds of galaxies and clusters. Tiny fluctuations in this radiation show where matter would clump, where gravity would gather gas and dust, and ultimately where stars and planets would form. It is a snapshot of the universe when it was only 380,000 years old, a time when light could first travel freely through space. This radiation is a whisper from the beginning, echoing across billions of years to reach us. Time itself is interwoven with the universe's expansion. The further we look, the further back we see. Observing galaxies billions of light years away is observing them as they were billions of years ago. In a sense, our telescopes are time machines, revealing the history of the cosmos as clearly as any historical record on Earth. By studying these distant objects, astronomers reconstruct the life story of the universe, its rapid growth, the formation of stars and galaxies, the ignition of the first black holes, and the gradual assembly of the cosmic web. And yet, even as we uncover these grand patterns, mysteries remain. Dark matter, the invisible substance that outweighs ordinary matter by roughly 5 to 1, binds galaxies and clusters together. We cannot see it, touch it, or directly detect it, but we observe its gravitational effects everywhere. Without dark matter, galaxies would fly apart, stars would scatter, and the universe would look entirely different. Its existence is undeniable, yet its nature remains elusive, a cosmic puzzle we may only partially solve in our lifetimes. Cosmologists also wonder about the fate of all light and matter. Stars burn their fuel and die, galaxies consume gas, and black holes slowly evaporate over unimaginable timescales. Even protons themselves, once thought stable, may decay over quadrillions of years. The universe is a story of birth, change, and slow, inevitable decay, a cycle writ large across space-time. It is humbling to realize that everything we know, every star in the sky, every planet and moon, is part of this grand, impermanent process. Yet there is beauty in this vastness and impermanence. The universe is not chaotic. It is structured, patterned, and logical, even when incomprehensibly large. Cosmic filaments of galaxies stretch across hundreds of millions of light years, separated by immense voids. Gravity sculpts matter into clusters, stars, and planets. Even dark energy follows rules, influencing the expansion in ways that can be measured and studied. The universe is both mysterious and knowable, infinite yet accessible to curiosity and understanding. On the tiniest scales, quantum fluctuations may influence the cosmos. Even empty space seethes with virtual particles, temporary manifestations of energy that flicker into and out of existence. These fluctuations, imperceptible to the human eye, may have seeded the structure of the universe itself, influencing the distribution of matter on the largest scales. The universe, it seems, is interconnected across scales from the subatomic to the galactic, from the first fraction of a second to its eventual fate billions of years hence. And yet, despite all our knowledge, much remains unknowable. We can observe galaxies, detect cosmic radiation, and measure expansion, but the true nature of dark energy, dark matter, and the ultimate fate of the universe remain shrouded in mystery. Each discovery raises new questions, inviting curiosity, humility, and wonder. The universe is vast, ancient, and alive with processes both beautiful and deadly, reminding us of the incredible scale of reality compared to the small, brief flicker of human existence. As you drift towards sleep, consider this. The universe is expanding around you even now. Galaxies you will never see are moving away, stars are forming and dying, and black holes are shaping the structure of the cosmos. Every particle of matter, every photon of light, and every whisper of gravitational waves is part of a vast, interconnected story. The universe is at once terrifyingly immense and intimately ordered, a reminder that even in the silence of the night sky, forces unimaginably powerful are at work. And here is the final thought to carry into your dreams tonight. The universe began in a fiery, dense state, has expanded for over 13 billion years, and continues to grow at an accelerating pace. We are observers in a cosmic story that stretches across time and space, witnessing forces and phenomena that are almost beyond comprehension. How will it all end? Will the universe grow colder and emptier, collapse, or continue indefinitely in a vast, accelerating expanse? The answers remain unknown, and perhaps that is part of the universe's quiet, enduring beauty.